So far, we have studied 5 different elements of symmetry. First one was identity, which was encompassing all the points in the molecule and around it. Second one was axis of symmetry, which was composed of one line. Means what will be the common in that identity and axis? A line will be common. Third one was plane of symmetry. It is a lamina. It is a cutting of the molecule into equal halves. So what can be the common in the plane, line and identity? Considering all possibility, at least one point will be common. Fourth one was center of inversion, a point present at the center of the molecule. Means what is the common among all? A point is common. Fifth one was improper axis of rotation. It also encompasses dual mode elements. One was axis, another was plane. Among all those 5, one thing is common, and that is point. So, there is a point in studying that point. All operations do pass through one point. Means operations are collected at one point. That point where all operations are grouped, all elements are grouped, which can describe all possible operations. It's called as point group. Out of the various types of point groups, I like to discuss here only 2 types of point groups. One cyclic and other dihedral. How to know them? How to categorize them? How to assign them? That we are studying. For that, a basic knowledge of principal axis, subsidiary axis, types of planes, horizontal, vertical or dihedral, that much concept at least should be known to you. Now I tell you one formula. Principal axis has with one order, say n is a order. Subsidiary axis, number of subsidiary axis, that may be the any number x, y, z or n also may possible. And planes we label as sigma h means horizontal, sigma v means vertical, sigma d means dihedral. So rule is, if order of the principal axis n is equal to number of subsidiary C2 axes, then point group type is dihedral means capital D. Otherwise, time being remember capital C. I repeat the formula. If order of the principal axis n is equal to number of subsidiary C2 axes, then capital D or else capital C. This is the first point of distinguishing the point groups or labeling the point groups. After the C or D categorization, we need to represent order of the principal axis. Just now I said, what was the order of the principal axis? N. So capital C or capital D that we have sought out from the operations possible, followed by as a suffix we need to write order of the principal axis N. So what will be the representation now? If it is a cyclic kind of point group, then Cn will be the representation. If dihedral kind of point group, then Dn will be the representation. But just wait, yet we have not completed the labeling. Afterwards, types of plane present in the molecule will decide the further nomenclature. So 3 planes, horizontal, vertical and dihedral. Among them, a superior plane, powerful plane, which we need to emphasize, which we need to mention is horizontal. Second is dihedral and third one is vertical. While arranging in a group, arranging in a collection or gathering the all operations, we were considering vertical first, then dihedral. But here while labeling, dihedral will come first, then vertical. That is a priority. Means, suppose if all three kinds of planes are present, then you will label it as H, horizontal plane. Although if horizontal remain present, then there is no question. We need to mention H there. Where should we mention that? That Cn or Dn that we found, no? There, H will follow that N. So it can be now CNH or it can be DNH. But suppose horizontal plane is not there. Only two planes are there, vertical and dihedral. Then who has a priority? Dihedral has the priority. So there we will represent it as C and D, which is not possible, but understand. And other D and D. For cyclic point group, existence of dihedral plane is not possible. It means C and D is not possible symmetrical point of view. But suppose dihedral plane is not there, horizontal plane also is not there, only vertical plane is there. No option, no choice, we need to represent it as V. So it can be C and V or D and V. Here, existence of only vertical plane impossible for dihedral point group. It means D and V as a point group is not possible symmetrically. The point groups which are in your syllabus are C2V, C3V, C2H, D3H, C infinity V, D infinity H. So among these C and D category with vertical and horizontal planes, point groups are included in your syllabus. Dihedral plane is not included, but I had informed to you what is that dihedral plane. Here we are discussing point group D infinity H. The label of point group tells us a lot. What it informs, which principal axis will present? Right, C infinity. Capital D letter is used for what? It is a collection of those operations where number of C2 axes, number of subsidiary C2 axes is equal to order of principal axis. Here order of principal axis is infinity. So number of subsidiary axes will be infinity. Is the second information given by this label. And third, in this collection of symmetry operations, there should be at least a horizontal plane. Other kinds of planes are possible, may or may not be. But here, especially in this point group, they do exist. But from label, from our general understanding of label, we can say there is a horizontal plane present or there exists horizontal plane. Now let us see the suitable examples for this point group and let us understand gathering or collection of all symmetry operations for this point group. First example that I like to consider here is of hydrogen molecule. See here, two hydrogen atoms are represented by white color, and between those two hydrogens there is a bond. Now, as usual, for any molecule, basic trivial operation exists. Which one is that? Identity. Yes, identity first, comma. Is there any axis of higher order along hydrogen-hydrogen bond? What is the name of that axis? Right, C infinity. How do we represent the possible operations around C infinity? Double C infinity operations with variant angle phi, where phi is greater than 0 but less than pi. And about that in detail I discuss many where. Afterwards, a C2 operation, only one C2 operation. Actually, this C2 operation is due to coinciding C2 axis to C infinity. So this is a generated from C infinity operation only. But it is a need for us to represent it separately. Therefore, it is represented here. Are there any axes which are perpendicular to the bond? Yes, there are C2 axes. Infinite number of C2 axes we can find. But see the way of representation. Correct way of representation. Infinite number of C2 operations with variant angle per phi plus pi by 2. Per phi is an angle considered for vertical plane. In C infinity V point group, you came across that term. Now for this point group also for vertical plane later on we are considering that, and to that plane we are considering C2 axis perpendicular. Angle of variation will be per phi plus pi by 2. It is just the notion. It is just the consideration. It is just the protocol or convention you can say. So how do we represent infinite number of C2 operations? Infinite C2 with variant angle per phi plus pi by 2. Afterwards, there is center of inversion as an element. An operation, first inversion operation I1. We simply represent it as I. After that, is there any horizontal plane? Is there a plane perpendicular to hydrogen bond? Is there a plane perpendicular to C infinity as a principal axis? Yes. We can cut this hydrogen molecule keeping a lamina plane perpendicular to the hydrogen bond and passing through center of the hydrogen. What is the name of that plane? Horizontal plane. So I represented there sigma h as an operation. Afterwards, is there any improper axis of rotation? Yes, whatever our C infinity principal axis is there, itself can become an improper axis of rotation. Actually, very large number of operations are possible for proper axis as well as improper axis of rotation. Because angle of variation is very small, that is phi. So angle of variation will be same as was there for axis, and representation also nearly same. How are we representing? Double the S infinity operations with variant angle phi. See here, number is infinite. Variation is very small, and therefore it doesn't make a change in the number. Infinite number of possible operations for proper axis of rotation, and for improper axis of rotation, rotoreflection also, infinite number of operations are possible. Students, are you following? Afterwards, last operation possible, that's a vertical plane. We can cut this hydrogen molecule along hydrogen bond, and simple change in the variant angle we can do. That variant angle we represent as per phi, that we did for C infinity V point group, and there I had given explanation. Infinite number of such vertical planes are possible, so operations are also infinite. So how is our representation? Infinite number of sigma V operations with variant angle per phi. And what is the range of per phi? Per phi is equal to or greater than 0 and less than pi. Rationale behind that already I discussed in the various videos. If I gather all the possible elements, the number is huge, number is large, number is uncountable, indefinite. So, order of the point group H is equal to infinity. Are you following this example? Some critical kind of the presentation is here. Understand the angles of variations. Okay, fine. Let us see what are the other molecules which show this point group D infinity H. The other example is carbon dioxide. See, the molecule is represented there. Carbon by gray color and oxygens by blue color. There are double bonds between carbon and oxygen. It is a linear molecule. There is a horizontal plane. There is a center of inversion, which was not there in C infinity V point group. So all possible operations are represented. First, identity. Second, double the C infinity operations with angle of variation phi. One of the C2 operation from that C infinity axis. Infinite number of C2 operations with angle of variation per phi plus pi by 2. Center of inversion operation. Horizontal plane. Reflection operation. Double the S infinity operations with angle of variation phi and infinite number of vertical planes with angle of variation per phi. Here phi is greater than 0 but less than pi and per phi is greater than or equal to 0 but less than pi. Total number of operations possible H is equal to infinity. Is this molecule clear? Now it's a last molecule, XeF2, xenon difluoride, linear molecule. By green color, fluorines I have represented here, and by yellow color, xenon is represented. Structure is same like hydrogen. Structure is same like carbon dioxide. Operations are also same. So point group also is same. Only the purpose to furnish this example is to broaden your vision about the arrangement of the atoms. Various examples let you know. So operations are same. Identity as usual. Along the bonds, there is a C infinity axis. From that C infinity, one of the coinciding axis C2 and C2 operation we are representing. Perpendicular to the bond, we can consider C2 axis and the variation of angle conventionally we are considering perpendicular to the angle of variation for vertical plane and for vertical plane it is per phi. Then for C2 axis the angle of variation will be per phi plus pi by 2. There is a center of inversion, so inversion operation. There is a horizontal plane, so reflection through that horizontal plane. Whatever the C infinity axis is there, itself is the S infinity axis. Infinite number of operations are possible, but the way of presentation is same as like for the axis. Double the S infinity operations with angle of variation phi. And at last, infinite number of the vertical planes are there. Angle of variation is per phi. Here, phi is greater than 0 but less than pi, while per phi is greater than or equal to 0 but less than pi. Total infinite number of operations are possible. Somewhat critical molecule. Somewhat way of presentations are difficult, but I tried my level best to explain. If it is not clear, you can see the previous video of C infinity V. Before that, I had given the video of proper axis of rotation. Go through all videos. The concept will be what the very clear. So let us see the homework for this part. Students, you need to write the all possible operations for D infinity H point group. Collection of all operations I want. I want all operations which are in the set bracket and you have to write them in comment box. If symbol presentation is a problem, you can use a word for that, but write it. It is a somewhat interesting application of molecular symmetry, and you will learn a lot during representation of operations of this point group. Represent order of the group also. Is the homework clear? From next part, we will discuss molecular orbital theory for polyatomic species.